Have you ever stood outside on a clear night, staring up at the stars, and wondered what it would be like to witness the birth of a black hole? Picture this somewhere, right now, in the distant reaches of space. A star many times more massive than our Sun is reaching the end of its life. It doesn't just fade away, it doesn't quietly disappear. Instead, it explodes with such staggering violence that for a few blinding seconds, it outshines entire galaxies. This is a gamma-ray burst, the single most energetic event in the known universe. And if you think that sounds dramatic, just wait until you hear what's really going on. These cosmic fireworks are so powerful that in the time it takes you to blink, a single gamma-ray burst can release more energy than our Sun will produce in its entire 10 billion-year lifetime. To put that into perspective, imagine every star in the Milky Way, every planet, every speck of dust, all burning at once. Now, compress all that raw power into a laser-thin beam firing across the cosmos. That's the mind-bending scale we're dealing with. And while these explosions happen millions, even billions of light years away, the fact that we can detect them at all tells you just how unimaginably bright they truly are. But here's the wildest part: gamma-ray bursts aren't just cosmic oddities. They're messengers from the far edges of space and time, carrying secrets about how the universe works, how stars live and die, and even what might happen when the fabric of reality itself gets stretched to its limits. Some of these bursts come from colliding neutron stars, others from hypernova supernova on steroids. And if one happened too close to Earth, well, let's just say we wouldn't be here to talk about it. So buckle up, because today we're diving deep into the science behind these spectacular explosions, uncovering how they work, why they matter, and what they reveal about the most extreme corners of the cosmos. This isn't just a story about distant flashes in the dark. It's a glimpse into the very forces that shape existence itself. Gamma-ray bursts are the universe's ultimate flashbang, short, devastating blasts of pure energy so powerful they briefly outshine everything else in the cosmos. These aren't just distant flickers of light. They're the brightest, most violent explosions since the Big Bang itself, packing more punch into a few seconds than most stars release in their entire lifetimes. And what's erupting isn't just any light, it's gamma rays, the highest energy form of radiation, invisible to our eyes but capable of piercing through solid lead like it's tissue paper. The wildest part, we stumbled onto them entirely by accident. Back in the 1960s, at the height of the Cold War, the United States launched a fleet of satellites called Vela. Their mission was simple: watch for telltale gamma-ray flashes that might signal secret nuclear tests in space. But instead of catching Cold War secrets, these satellites picked up something far more mysterious: bursts of energy coming not from Earth but from deep space. Scientists were baffled. Some thought they might be Soviet weapons. Others wondered if they were signals from an advanced alien civilization. But the truth was stranger than fiction. These were natural cosmic disasters on a scale we'd never imagined. The first bursts were so unexpected that researchers spent years double-checking their instruments. The energy signatures made no sense. How could something so brief produce more power than a million supernova? And why were they coming from random directions in the sky with no pattern or warning? It took decades of detective work and a revolution in space telescope technology to finally crack the case. Today, we know these bursts are the death cries of massive stars or the catastrophic collisions of ultra-dense stellar corpses. But back then, they were just eerie, unexplained blips on a military satellite screen, a cosmic mystery written in gamma rays. What makes these explosions so shocking isn't just their raw power, but how they defy our everyday intuition about how the universe works. Take a typical burst, let's say one lasting about 2 seconds. In that blink of cosmic time, it unleashes enough energy to boil away entire planets, all focused into a narrow beam traveling at nearly the speed of light. If you were unlucky enough to be in that beam's path, even thousands of light years away, it would strip the ozone from your planet's atmosphere in seconds. And yet, because the beams are so tightly focused, we only see them when they happen to point directly at Earth, like catching the glare of a lighthouse from across an ocean of stars. Gamma-ray bursts aren't all created equal. Some are cosmic lightning strikes, over in a flash, while others rage like wildfires across the sky. The key to unlocking their secrets lies in their heartbeat, the duration of their pulse. Split-second blips lasting less than 2 seconds are the universe's way of signaling a violent merger, two neutron stars spiraling into each other in a dance of destruction. These short bursts are like the final scream of matter squeezed into oblivion, releasing a torrent of gamma rays as the stars collapse into a black hole. But when a burst lingers longer, stretching for minutes or even hours, that's the signature of a dying titan. A star so massive its death throws rip through space like a supernova on overdrive. Take short bursts first. Imagine two city-sized neutron stars, each so dense a teaspoon of their material would weigh 1 billion tons. Locked in a gravitational embrace, they inch closer over millennia until, boom, they collide. The impact isn't just an explosion, it's a factory for the universe's heaviest elements, forging gold, platinum, and uranium in the fireball's wake. These mergers are so precise in their destruction that the gamma rays they emit are fleeting but razor-focused, like a flashlight beam aimed straight at Earth. And in 2017, we didn't just detect one, we saw it in gravitational waves, light, and gamma rays, confirming these crashes as cosmic gold mines. Long bursts tell a darker, grander story. Here, a star 20 to 30 times more massive than our Sun reaches the end of its life not with a whimper, but with a hypernova, a supernova's bigger, angrier sibling. As the star's core collapses, it doesn't just explode outward, it funnels its energy into twin jets piercing through the star's poles at near light speed. These jets, hotter than 1 trillion suns, are the gamma-ray burst itself. If one of those jets points at us, we see the burst as a long, drawn-out spectacle, sometimes glowing for hours in X-rays and visible light. These are the universe's demolition derbies, so bright they've been spotted from over 13 billion light-years away, nearly the edge of observable space. What's fascinating isn't just their origins, but how these durations act as cosmic fingerprints. Short bursts are clean, surgical events neutron star mergers leave behind little debris like a controlled implosion. Long bursts, though, they're messy, chaotic, with remnants glowing for weeks as radioactive elements decay. And here's the twist, some long bursts might not even come from hypernova, but from rare collapsars, stars so massive they skip the explosion entirely and dive straight into black hole formation. The universe, it seems, has more than one way to craft these brilliant catastrophes. So why does this split matter? Because each type is a window into different extremes of physics. Short bursts teach us about matter crushed beyond recognition, while long bursts reveal how stars push the limits of size and energy. Together, they're cosmic laboratories, places where the laws of nature are stretched, shredded, and rewritten in gamma-ray fire. And as we watch these distant flashes, we're not just spectators, we're detectives piecing together the life and death of the universe's most extreme objects, one burst at a time. To grasp the sheer power of a gamma-ray burst, think of the Milky Way, our home galaxy, with its hundreds of billions of stars, each pouring out energy over billions of years. Now imagine all that light, all that brilliance concentrated into a single burst lasting barely a few seconds. That's the scale we're talking about. A typical gamma-ray blast can pump out more energy in its brief lifetime than our entire galaxy emits across 100,000 years. It's like comparing a matchstick to a supernova, except in this case, the matchstick briefly burns brighter than everything else in the universe combined. But let's make it even more mind-bending. A regular supernova, the explosion of a massive star, is already one of the most violent events in nature. At its peak, it can shine as brightly as an entire galaxy for weeks. Yet even that pales next to a gamma-ray burst, which outshines a supernova by a factor of 100, sometimes even 1,000. Picture a stadium floodlight next to a nuclear bomb. That's the difference in raw, unfiltered power. And while the sun's solar flares can unleash enough energy to disrupt satellites and power grids, they're mere sparks compared to the inferno of a gamma-ray burst. A single second of a GRB's fury contains more energy than the sun will produce in its entire 10 billion-year lifetime. What makes these bursts so impossibly bright isn't just the amount of energy, it's how they deliver it. Unlike a supernova, which explodes in all directions like a bursting balloon, gamma-ray bursts channel their energy into twin jets narrower than a laser beam. All that apocalyptic force is focused into a corridor of destruction just a few degrees wide, meaning if you're not directly in the line of fire, you'd barely notice it. But if you are, that concentrated beam punches through space with the precision of a cosmic blowtorch, heating gas clouds to billions of degrees and accelerating particles to within a hair's breadth of light speed. We've seen bursts so luminous they're visible from the edge of the observable universe over 13 billion light-years away. To put that in perspective, the light from those explosions left its source before Earth even existed. Yet when it finally reached us, it was still bright enough to outshine galaxies closer to home. That's not just impressive, it's physics pushed to its absolute limit. And while we've never witnessed a burst up close, thankfully, simulations suggest standing even 1,000 light-years away from one would feel like standing next to a nuclear detonation, except instead of a fireball, you'd be bathed in enough gamma rays to strip the atmosphere off a planet. So why don't we see these bursts lighting up the night sky constantly? Simple, they're rare, and they don't last. A galaxy like ours might see just one every 100,000 years. But that rarity only makes them more extraordinary. Each burst we detect is a fleeting, violent masterpiece, a glimpse into the universe's most extreme physics, where matter, energy, and gravity collide in ways we're only beginning to understand. And when you realize that something so brief can outshine everything else in existence, even for a moment, it makes you wonder what else is out there waiting to be discovered. When a star 30 times more massive than our Sun reaches the end of its life, it doesn't just fade away, it goes out with a violence so extreme it redefines the word explosion. This is the birth cry of a long gamma-ray burst, a spectacle born from the death throes of a cosmic titan. Here's how it happens. Deep inside the star, the core runs out of fuel, causing gravity to win its endless tug of war. In an instant, the core collapses inward at a quarter the speed of light, compressing matter so tightly it forms a black hole. But the story doesn't end there. This is where the real chaos begins. As the core vanishes into oblivion, the star's outer layers, suddenly without support, come crashing down like an avalanche. But not all of that material falls into the black hole. Some of it gets caught in a whirlpool of superheated plasma, spinning so fast it generates magnetic fields trillions of times stronger than Earth's. These fields act like cosmic particle accelerators, funneling debris into two narrow jets that blast outward from the star's poles at 99.9% the speed of light. These jets aren't just fast, they're hotter than a billion suns, and when they punch through the dying star's surface, they unleash the gamma-ray burst we see from across the universe. What's terrifying and mesmerizing is how efficient this process is. The entire sequence from core collapse to jet eruption takes mere seconds. The jets themselves are so focused that if you were to widen one to the size of a straw, it could reach from Earth to the Moon with almost no spread. And the energy, a single jet can outshine its host galaxy by a factor of 1,000,000. All while carrying enough kinetic energy to fling entire solar systems into deep space. But here's the twist, we only see these bursts when one of those jets happens to point directly at Earth. It's like being in the front row of a cosmic laser show, except the lasers are capable of sterilizing entire planets. The rest of the universe sees nothing more than a faint afterglow, if anything at all. That's why long bursts are so rare in our observations. For every one we detect, there are hundreds, maybe thousands, firing off in other directions unseen. The aftermath is just as dramatic. As the jets plow through interstellar gas, they create shockwaves that glow for weeks in X-rays and visible light, leaving behind a fading fingerprint of the catastrophe. Sometimes the dying star's outer layers explode outward in a hypernova, a supernova on steroids, creating a nebula laced with heavy elements forged in the explosion. And at the center, a newborn black hole, silent and dark, the only remnant of a star that once burned brighter than a galaxy. What's astonishing is how much these events teach us. Long gamma-ray bursts are cosmic signposts, marking the deaths of the universe's most massive stars and the birth of black holes. They're also gold mines for physicists, offering glimpses into how matter behaves under conditions impossible to recreate on Earth, where magnetic fields twist spacetime itself and particles reach energies beyond anything our largest colliders can produce. And there's a sobering thought buried in all this brilliance. If a long gamma-ray burst happened within a few thousand light-years of Earth, its jets could strip away our ozone layer, triggering mass extinctions. Some scientists even suspect one might have played a role in the Ordovician extinction 450 million years ago. It's a reminder that the universe isn't just awe-inspiring, it's also indifferent, capable of creating and destroying on scales we can barely comprehend. Yet for all their destructive potential, these bursts are also beacons. They illuminate the far reaches of the cosmos, helping us map the early universe and test the laws of physics at their extremes. Each one is a message in a bottle tossed across billions of years, a fleeting scream of light that tells the story of a star's death, a black hole's birth, and the violent, beautiful machinery of the cosmos. Now let's shift our focus to the universe's most spectacular smashing events, neutron star collisions. These aren't just cosmic fender benders, they're cataclysmic mergers where two ultra-dense stellar corpses spiral together in a final, fatal embrace, unleashing both short gamma-ray bursts and something even more precious, kilonovae, the cosmic forges where much of the universe's gold and platinum are born. Picture two neutron stars, each no bigger than a city yet weighing more than our sun. They're so dense that a single sugar cube of their material would outweigh Mount Everest. Locked in orbit by gravity, they inch closer over millennia, radiating energy as ripples in space-time gravitational waves. As the final moments approach, they whip around each other hundreds of times per second, stretching and distorting like taffy until crash. The impact is beyond anything in human experience. Temperatures soar to trillions of degrees, atoms are shredded into quark soup, and tidal forces eject glowing streams of neutron-rich material into space at nearly light speed. That's when the magic happens. The ejected material, bathed in the merger's insane heat and pressure, undergoes rapid neutron capture, a process called the R process. Here, atomic nuclei gobble up free neutrons faster than they can decay, climbing the periodic table in seconds to form heavy elements like gold, platinum, and uranium. The resulting explosion, the kilonova, glows with a distinctive reddish hue as these freshly minted elements undergo radioactive decay. A single merger can produce hundreds of Earth masses of gold alone, scattering it across interstellar space like cosmic confetti. But the real game changer came in 2017. For the first time in history, astronomers didn't just see a neutron star merger, they heard it. When gravitational wave detectors LIGO and Virgo caught the spacetime ripples from an event dubbed GW 170817, telescopes worldwide swung into action. What followed was unprecedented. A short gamma-ray burst detected just 2 seconds after the merger's gravitational signal, followed by days of kilonova glow in visible light, X-rays, and radio waves. This multi-messenger astronomy event confirmed theorists' wildest dreams that neutron star collisions were indeed the source of both short GRBs and Kilonovae. The data was like opening a treasure chest. Spectra revealed fingerprints of heavy elements, proving Kilonovae as cosmic gold factories. The GRB's energy matched predictions of jets launched by the newborn black hole formed in the merger. Even the afterglow's behavior, how it brightened and faded, gave clues about the jet's structure and the environment around the collision. But perhaps most mind-blowing was the sheer coordination it revealed across the universe. Gravitational waves traveling at light speed, followed almost instantly by gamma rays, then the slower building light show of the kilonova. Here's why this matters beyond scientific curiosity. Nearly all the gold in your jewelry, the platinum in catalytic converters, even the uranium in nuclear reactors, these elements likely owe their existence to Kilonovae. Ordinary supernova can't forge such heavy atoms. It takes the neutron-rich chaos of a stellar merger to do that. So in a very real sense, these cataclysms are the universe's alchemists, turning the debris of dead stars into the rare materials that make our technology and even life as we know it possible. Yet for all their brilliance, Kilonovae are fleeting. Within weeks, the glow fades, leaving behind only a faint nebula and a black hole. But the echoes of that 2017 event continue to reshape astrophysics. It proved that gravitational waves could lead us to hidden cosmic wonders, that gamma-ray bursts have multiple origin stories, and that the universe manufactures its heaviest elements in the most violent workshops imaginable. The next time you hold a gold ring, remember, it may have begun its existence in a fireball hotter than a supernova, forged in the crucible of colliding stars billions of years ago. The moment a gamma ray burst's initial flash fades, the real detective work begins. That split-second explosion of gamma rays is just the opening act. What follows is a slowly fading afterglow, shining in X-rays, visible light, and radio waves for days or even weeks. Think of it like a flashlight beam cutting through thick fog. The initial burst is the moment you flip the switch, blindingly bright but fleeting, the afterglow. That's the light scattering off water droplets, lingering long enough to trace the beam's path back to its source. This fading glow is more than just cosmic leftovers. It's a breadcrumb trail leading straight to the burst's origin. When the ultra-relativistic jets from a GRB plow into surrounding gas and dust, they create shock waves that heat the material to millions of degrees. Like a car's tires screeching against pavement, this interaction emits radiation across the electromagnetic spectrum, first X-rays, then visible light, finally radio waves as the shock waves slow and cool. Telescopes worldwide race to capture this sequence because each wavelength reveals another clue. X-rays pinpoint the jet structure, optical light uncovers the host galaxy, and radio emissions map the debris field's expansion. Take GRB 030329, a burst so distant its light traveled for 11 billion years before reaching Earth. Its afterglow, visible for nearly 2 months, allowed astronomers to trace it to a tiny dwarf galaxy, proof that these explosions can happen even in the universe's dimmest corners. Another, GRB 130427a, left an X-ray glow so persistent it was detected for over 700 days, hinting at an unusually long-lived central engine, likely a newborn black hole still greedily feeding on stellar debris. The afterglow's behavior is also a physics playground. The way it fades, whether steeply or in plateaus, betrays the jet's energy and how tightly it's focused. A sudden brightening might mean the jet has encountered a dense gas cloud, while a skewed color shift could reveal interstellar dust bending the light like a prism. And sometimes the afterglow does the unexpected. In 2019, GRB 190814b's visible light glow flickered wildly weeks later, as if someone had reignited the engine. The culprit, the black hole at the burst's heart, belching out fresh energy as it swallowed another chunk of the doomed star. What's staggering is how much we've learned from these cosmic echoes. Before afterglows were discovered in the late 1990s, GRBs were just mysterious blips on a screen. Now they're Rosetta Stones, decoding everything from the birth rates of early galaxies to the speed of spacetime itself. And with every new afterglow we catch, the universe leaves another fingerprint, one that glows just long enough for us to read it. Catching a gamma-ray burst in action is like trying to photograph lightning with a Polaroid. You've got to be fast, prepared, and incredibly lucky. That's where NASA's SWIFT satellite comes in. Launched in 2004, SWIFT is the universe's ultimate rapid response detective. The moment its Burst Alert telescope detects a GRB, the satellite can swivel autonomously in under a minute to point its X-ray and ultraviolet telescopes at the explosion. This agility is revolutionary. Imagine a security camera that not only senses motion but instantly zooms in on the intruder while simultaneously calling the police. But SWIFT doesn't work alone. It's part of a global network anchored by Fermi, NASA's Gamma-Ray Space Telescope. While SWIFT specializes in speed, Fermi excels in sensitivity, detecting higher energy gamma rays with its large area telescope. Together, they're the perfect tag team. Fermi often spots the initial burst, while SWIFT pivots to capture the afterglow. Within seconds of a detection, automated systems beam coordinates to observatories worldwide, triggering a synchronized chase. Telescopes from Chile to Hawaii swing into action, hunting the fading glow like cosmic bloodhounds. The real magic happens on the ground. Instruments like the Very Large Telescope in Chile or the Keck Observatory in Hawaii use their massive mirrors to dissect the afterglow's light, revealing the burst's distance, chemical fingerprints, and even the nature of its host galaxy. Meanwhile, radio telescopes like the Atacama Large Millimeter Array tune into the shockwaves rippling through interstellar gas. This global scramble turns fleeting bursts into enduring scientific treasures. Every photon captured helps unravel the physics of these extreme events. One of the most dramatic examples of this teamwork was GRB 080319b in 2008. SWIFT detected the burst at 4:31 a.m. Eastern Time, and within 75 seconds it had relayed coordinates to ground telescopes. Just 19 minutes later, the Very Large Telescope in Chile snapped the afterglow's spectrum, revealing the burst had occurred 12.8 billion light-years away, making it, at the time, the most distant object ever identified. Without this rapid response web, that groundbreaking discovery would have vanished into the cosmic background noise. The data from these missions doesn't just satisfy curiosity, it rewrites textbooks. Fermi's observations proved some bursts accelerate particles to energies 100 times greater than the Large Hadron Collider. SWIFT's ultraviolet eyes revealed how GRBs can ionize gas across entire galaxies, leaving behind interstellar scars. And when gravitational wave detectors like LIGO catch a neutron star merger, it's often SWIFT or Fermi that pinpoints the accompanying gamma-ray flash, turning a ripple in spacetime into a full-blown cosmic crime scene. What's next? New players like the upcoming European Space Agency's Theseus mission aim to spot even fainter, more distant bursts, while ground-based telescopes like the Giant Magellan Telescope will dissect their afterglows with unprecedented precision. Each upgrade tightens the net, ensuring that the next time the universe unleashes one of its brightest explosions, we'll be ready not just to witness it but to understand it. On October 9, 2022, the universe threw a tantrum so spectacular that astronomers are still reeling from the data. That's when gamma-ray burst 221009 lit up the sky, a cosmic flare so intense it blinded sensors across the solar system despite erupting from a staggering 2.4 billion light-years away. Dubbed the BOT brightest of all time, this explosion rewrote the record books before most telescopes could even swing into position. The numbers defy belief. At peak brightness, it pumped out 18 tera-electronvolts of energy. That's photons with over 1 trillion times the energy of visible light, making it the most energetic gamma-ray burst ever recorded. Even more mind-bending, the afterglow lingered for months, outshining its host galaxy by a factor of 1,000,000. Satellites like Swift and Fermi, built specifically to handle GRBs, were momentarily overwhelmed as their detectors slammed into the red line. One scientist described it as trying to measure a hurricane with a rain gauge built for drizzle. But what made this burst the undisputed heavyweight champion? It all comes down to a freakish alignment of physics and geometry. Unlike most GRBs, whose jets are pencil-thin, 221009A's beams were unusually wide while still maintaining insane energy density, like a fire hose set to light speed. That rare combination meant Earth got a direct hit from not just the core jet, but also the surrounding cascade of energized particles. We weren't just glimpsing the lighthouse beam, we were swimming in its reflection. The aftermath became a goldmine for astrophysics. X-ray observations revealed how the jet plowed through interstellar gas like a bulldozer, creating shock waves that acted as particle accelerators. Radio telescopes caught the debris field expanding at 99% light speed, while ultraviolet spectra hinted at heavy elements being forged in real time. Even more startling, some models suggest the black hole born from this cataclysm may have briefly spun faster than any object in the known universe, a cosmic top nearing the literal limits of angular momentum. Yet for all its fury, 221009 carries a humbling message. That burst occurred when Earth's continents were just cooling from the Proterozoic era, before multicellular life existed. Its light spent 2.4 billion years crossing the cosmos, only to flicker across our detectors for a few minutes. And here's the kicker: given how GRBs disperse their energy, there could be far brighter ones already en route, their light still traveling through the void. The universe, it seems, always keeps a few aces up its sleeve. What's certain is this: every record-breaking burst forces us to reconsider what's possible. 221009 wasn't just brighter. It was a masterclass in extremes, proving that even our wildest models still underestimate the universe's capacity for violence. And as new telescopes come online, capable of spotting even fainter echoes from the cosmic dawn, one question lingers: how much brighter could the next BOT be? The answer might already be racing toward us, a flash of gamma rays scribbling its reply across the dark. Gamma ray bursts don't just shatter energy records, they're also cosmic yardsticks, helping us measure the vast stretches of the universe with astonishing precision. Picture this: every burst's light carries a hidden message in its color, stretched over billions of light years as it travels through expanding space. This phenomenon, called redshift, turns GRBs into natural rulers. The further away they are, the more their light shifts toward the red end of the spectrum. But what makes them truly special isn't just their distance, it's their reliability. Unlike other cosmic beacons that flicker unpredictably, long gamma-ray bursts follow a consistent pattern in their luminosity, making them among the universe's most trusted measuring tapes. Here's how it works. When astronomers catch a long GRB, they don't just see a flash, they see a fingerprint. The burst's afterglow reveals how much its light has redshifted, which tells us how far it's traveled. But distance alone isn't enough. To map the universe's expansion, we need to know how bright the burst should be at its source. That's where long GRBs shine, literally. Researchers noticed that these bursts, despite their chaos, share a predictable relationship between their peak energy and total output. It's like finding out every lighthouse in the ocean emits light at the same intrinsic brightness. Suddenly, you can calculate distances just by how dim they appear from shore. This consistency transforms GRBs into standard candles, similar to how supernovae were used to discover dark energy. But GRBs have a unique edge: they're visible from much farther away. The most distant burst ever recorded, GRB 090429b, erupted just 400 million years after the Big Bang, so remote that its light redshifted by a factor of 9.4. Traditional supernova can't compete with that reach. By stacking these measurements, astronomers trace the universe's expansion rate across cosmic time, spotting subtle twists in the fabric of spacetime itself. Yet the real power of GRBs lies in their versatility. They're not just distance markers, they're time machines. When we analyze a high redshift burst, we're glimpsing the universe in its adolescence, a period when galaxies were forming and the first stars were igniting. The Afterglow spectrum acts like a cosmic barcode, revealing the composition of ancient gas clouds and even the density of dark matter along its path. Some bursts have even helped test Einstein's theory of relativity over mind-bending scales, proving that light's speed remains constant whether it's traveled 1 million or 10 billion years. Of course, no tool is perfect. GRBs require careful calibration since their jets aren't all identical, but clever techniques like comparing the burst's brightness in different energy bands help filter out the noise. And with next-gen telescopes like the James Webb Space Telescope teaming up with gamma-ray detectors, we're poised to push these measurements further back in time than ever before. Every new burst sharpens our cosmic map, stitching together a clearer picture of how space stretches, galaxies evolve, and the universe grows colder with age. So the next time you hear about a gamma-ray burst, remember it's not just a flash in the dark. It's a beacon from the depths of time, whispering secrets about how vast the cosmos truly is and how far we've come in deciphering its grand design. Gamma-ray bursts aren't just spectacular explosions, they're windows into the universe's infancy, carrying light from an era before Earth, before the Milky Way, even before most stars as we know them existed. When we catch a burst from 12 or 13 billion light-years away, we're not just seeing a distant flash, we're witnessing the aftermath of some of the first stars to ever ignite in the cosmos. These titanic explosions illuminate a chapter of history called the Cosmic Dawn, a time when the universe was emerging from its dark ages, a murky period after the Big Bang but before starlight flooded space. Take GRB 090429b, detected in 2009. Its light traveled for 13.1 billion years to reach us, meaning it erupted when the universe was less than 600 million years old, a mere toddler by cosmic standards. That burst didn't just break distance records, it carried chemical fingerprints from the first generation of stars, monsters hundreds of times more massive than our Sun, made purely of hydrogen and helium. Their deaths seeded the cosmos with heavier elements, forging the raw materials for planets, life, and everything we know. But here's what makes these ancient bursts so invaluable. They pierce through the fog of the dark ages like a flashlight in a cave. For hundreds of millions of years after the Big Bang, the universe was filled with a thick haze of neutral hydrogen gas, absorbing ultraviolet light and keeping space pitch black. Then, around the time GRB 090429b exploded, something transformative happened. Radiation from the first stars and galaxies began ionizing that hydrogen, clearing the fog in an event called reionization. Gamma-ray bursts give us a front-row seat to that process. Their afterglows, passing through primordial gas clouds, reveal how and when the universe became transparent, like finding a fossilized air bubble in ancient amber. The clues lie in the light spectrum. As an afterglow travels through space, hydrogen gas imprints dark absorption lines at specific wavelengths. By measuring how those lines shift and deepen in high redshift bursts, astronomers can map the density and ionization state of gas across cosmic time. Some bursts even show signs of interacting with proto-galaxies, clumps of matter still coalescing into the structures we recognize today. It's like catching snapshots of a city under construction, with GRBs as the camera flashes. And there's another layer to this time travel trick. The very presence of gamma-ray bursts in the early universe tells us something astonishing about how quickly stars formed after the Big Bang. These explosions require massive stars, which in turn need dense gas clouds. The fact that we see GRBs so early suggests star formation was already in full swing within a few 100 million years of the universe's birth, far earlier than some models predicted. It's as if we dug up a medieval cathedral and realized humans were building skyscrapers in the Stone Age, but the real frontier lies even further back. Theorists dream of detecting a gamma-ray burst from population 3 stars, the mythical first stars, made purely of Big Bang remnants. These celestial pioneers would have lived fast, died young, and left behind black holes that might still power GRBs today. Spotting one would be like unearthing the Rosetta Stone of cosmic evolution, revealing the moment starlight first pierced the darkness. Every distant burst we find pushes our vision deeper into the past, turning these explosions into more than just fireworks. They're messages in a bottle cast adrift when the universe was learning how to shine, and now, against all odds, washing up on the shores of our telescopes. With each one decoded, we rewrite the origin story of everything. Let's talk about the elephant in the room. Could Earth ever get caught in the crossfire of one of these cosmic cataclysms? The unsettling truth is that if a gamma-ray burst happened within a few thousand light-years of us, the results would be catastrophic. The jet's intense radiation would act like a cosmic sandblaster, stripping away our ozone layer in a matter of seconds. Without that protective shield, ultraviolet radiation from the sun would bombard the planet, triggering mass extinctions, collapsing food chains, and turning the surface into a scorched wasteland. There's even evidence this might have happened before. Some scientists suspect a GRB could have contributed to the Ordovician extinction 450 million years ago, when 60% of marine life vanished mysteriously. But before you start building an underground bunker, here's the good news: the odds are astronomically low. Think of it like playing cosmic roulette, where the Milky Way structure is the house rules. Our galaxy spans 100,000 light-years, but most stars, and therefore most potential GRB progenitors, are concentrated in the crowded central bulge or the bustling spiral arms. We're tucked away in the quiet suburbs, the Orion Spur, where massive stars are rare and widely spaced. Statistically, a dangerous burst would need to occur within 6,000 to 8,000 light-years to affect us, but in our galactic neighborhood, stars that big are separated by hundreds of light-years on average. Even more reassuring, the universe is working in our favor. Long gamma-ray bursts, the most powerful kind, seem to prefer small, metal-poor galaxies, the cosmic equivalent of backwater towns where stars form from pristine hydrogen and helium. The Milky Way, by contrast, is a metropolis rich in heavier elements, making it harder for monster stars to reach the sizes needed for a hypernova. Simulations suggest we might see a threatening GRB once every billion years or so, and even then, the jet would have to be pointed directly at us, like winning the universe's unluckiest laser tag game. But what if, against all odds, a nearby star did go hypernova? Astronomers have their eyes on a few candidates like Eta Carinae, a volatile binary system 7,500 light-years away. If it collapses into a GRB, the jet's angle would be everything. Tilted just 5 degrees away from Earth, we'd barely notice. Dead center, we'd have front-row seats to an atmospheric apocalypse. Yet even Eta Carinae is more likely to produce a regular supernova, spectacular, but not ozone-destroying. The real takeaway isn't fear, it's perspective. Gamma-ray bursts remind us that we live in a dynamic, sometimes violent universe, but also one governed by statistics and physics that overwhelmingly favor our survival. For every distant flash we detect, there are countless others firing harmlessly into the void. Our planet has weathered 4.5 billion years of cosmic randomness, and the numbers suggest we'll keep dodging celestial bullets for billions more. So rather than worrying about GRBs, maybe we should marvel at them, proof that even in a universe capable of such destructive power, we've won the lottery simply by being here to watch. 450 million years ago, Earth's oceans teemed with trilobites, nautiloids, and early coral reefs until catastrophe struck. The Ordovician extinction wiped out 85% of marine species in a geological blink, leaving paleontologists scrambling for answers. While most mass extinctions have clear culprits, asteroid impacts, volcanic winters, this one remains shrouded in mystery. Enter the gamma-ray burst hypothesis, the idea that a nearby GRB could have unleashed a silent apocalypse without leaving a single crater. Here's how it might have happened. A jet from a GRB within 6,000 light-years would have bathed Earth in gamma and X-rays, splitting nitrogen and oxygen molecules in the upper atmosphere to create nitrogen dioxide, a compound that devours ozone. Within days, our protective shield would have thinned by 40% or more. Suddenly, the sun's ultraviolet radiation, usually filtered out, would have become a scalding torrent. Surface-dwelling plankton, the base of the marine food chain, would have died en masse. Deeper ocean creatures, shielded by water, might have survived initially until collapsing ecosystems starved them out. The fossil record eerily matches this scenario. Shallow water species suffered far worse than deep sea life during the Ordovician die-off, but here's where the debate ignites. While asteroid impacts leave iridium layers and craters, GRB evidence is circumstantial. Proponents point to isotopic anomalies in Ordovician rocks, like excess radioactive iron-60, that could hint at a stellar explosion. Critics counter that similar isotopes appear in periods without extinctions. More damningly, statistical models suggest a lethally close GRB hits Earth only once every billion years or so. The Ordovician event was one of 5 major extinctions, making GRBs an unlikely recurring villain. Compare this to the Cretaceous-Paleogene extinction, where the smoking gun is unmistakable. A 10-mile-wide asteroid left a 93-mile crater under Mexico's Yucatan Peninsula, scattering iridium worldwide and baking the atmosphere with vaporized rock. The aftermath, years of acid rain, global wildfires, and a nuclear winter effect, matches the fossil record's abrupt die-off. Asteroids also leave visible scars. Earth's surface preserves nearly 200 impact craters, while a GRB's atmospheric damage would vanish without trace. Yet the GRB hypothesis refuses to die, and for good reason. Unlike asteroids, which target random coordinates, GRBs preferentially threaten galaxies like the Milky Way's metal-rich core, where stellar densities are higher. Our solar system's current location is relatively safe, but Earth's position changes as it orbits the galaxy. 250 million years ago, during the Permian extinction, the worst ever, we were passing through a spiral arm, a stellar nursery ripe for hypernova. Intriguingly, that event also disproportionately affected UV-sensitive species. The takeaway: while asteroids dominate extinction headlines, the universe has deadlier weapons in its arsenal. GRBs remind us that cosmic threats aren't just lurking in our solar system's backyard, they're woven into the fabric of space itself, waiting for the wrong star to explode at the wrong time. For now, the odds favor asteroids as Earth's prime executioners, but in a galaxy where stars live fast and die violently, it's worth remembering, sometimes the greatest dangers come from light years away, invisible, unstoppable, and already on their way. Could an advanced civilization weaponize gamma-ray bursts? Science fiction loves this idea. Imagine a Death Star-style superweapon capable of unleashing cosmic destruction across star systems. But the brutal truth is that even a weak GRB would require energies far beyond anything humanity or any plausible alien empire could harness. Let's break down why. First, consider the math. A typical gamma-ray burst unleashes around 10 to the 44 joules of energy. That's a 1 followed by 44 zeros. To put that in perspective, all the nuclear weapons ever detonated on Earth combined release roughly 10 to the 18 joules. You'd need a quadrillion times that just to match a fraction of a GRB's output. Even if an alien civilization could harness the total energy output of their star for millennia, they'd barely scratch the surface. The universe operates on scales that make even the most advanced technology look like a child's firecracker. Then there's the engineering nightmare. GRB jets aren't just powerful, they're precision instruments. Natural bursts focus their energy into beams narrower than a degree wide, a feat requiring gravitational and magnetic fields stronger than anything we can replicate. Trying to artificially recreate that would be like threading a needle with a tsunami. And let's not forget the source material. You'd need to either collapse a star 30 times more massive than the Sun or smash two neutron stars together at relativistic speeds. Neither option lends itself to practical weapons testing, but here's where sci-fi gets creative. Some theorists speculate about stellar engines, megastructures that could, in theory, redirect a star's natural processes. Imagine tapping into a hypergiant's core collapse or nudging neutron stars into collision courses. It's not impossible, just hilariously impractical. The energy required to manipulate celestial bodies on that scale would dwarf the GRB itself, turning the whole endeavor into a cosmic Rube Goldberg machine. Even if you crack the energy problem, there's the issue of control. GRBs aren't precision tools, they're indiscriminate, like trying to assassinate a single person by detonating a continent. Any civilization capable of wielding that power would likely have far more efficient methods of destruction. Why bother with a gamma-ray burst when you could deploy self-replicating nanobots or relativistic kinetic missiles? Ultimately, GRBs remain nature's exclusive domain, a reminder that the universe holds monopolies on certain kinds of violence. They're not weapons, they're cosmic signatures written in gamma rays and gravitational waves. And perhaps that's for the best. If anything deserves to stay beyond the reach of civilizations, it's the power to mimic the universe's most destructive forces. So while sci-fi may keep dreaming of planet-cracking superweapons, real physics offers a humbling truth. Some things are too big, too wild, and too awe-inspiring to be anything but natural. The universe, it seems, will always hold the patent on ultimate destruction. Gamma-ray bursts have infiltrated pop culture like a stealthy cosmic phenomenon, sometimes accurate, often exaggerated, but always dramatic. Take the Avengers 2012, where Tony Stark name drops gamma radiation while tracking the Tesseract's energy signature. The film plays fast and loose with science, implying gamma rays could pinpoint an alien power source. In reality, GRBs are fleeting, distant, and involve energies that would vaporize any nearby tech. Not exactly ideal for interstellar GPS. Yet that single line tapped into something real. Gamma rays are the universe's most energetic fingerprints, even if Hollywood bends their purpose for plot convenience. Then there's Mass Effect, where the Andromeda Initiative's ARC ships use gamma-ray burst avoidance as a selling point for cryo-passengers. This one's closer to the truth. While the game simplifies the odds, a GRB striking a ship mid-flight is astronomically improbable. It acknowledges the genuine threat these beams pose to biology. In one chilling scene, a character describes a nearby burst sterilizing planets, a nod to the real-world extinction hypotheses. Mass Effect even gets the jet geometry right, depicting bursts as focused beams rather than omnidirectional explosions. But pop culture's most infamous GRB appearance might be the day the Earth caught fire, 1961. Where nuclear tests accidentally shift Earth's orbit, triggering solar storms and climate chaos. While the premise is pure fiction, the film accidentally predicted a real debate. Could human activity ever influence cosmic-scale events? The answer, thankfully, is no. GRBs operate on energies that dwarf anything humanity could unleash, making them nature's exclusive domain. Even video games like Destiny weave GRBs into lore, with the gamma ships of the Reef Fleet designed to harness cosmic radiation. Here, the fiction lies in scalability. No known material could contain or weaponize that energy without disintegrating. Yet the aesthetic nails something essential. GRBs feel apocalyptic, a quality that resonates with storytellers. What's fascinating is how these portrayals oscillate between cautionary tales and wishful thinking. For every scientifically grounded reference contacts realistic burst detection, there's a Thor, Ragnarok where gamma energy becomes a superhero's power source. But perhaps that's the point. GRB, in all their terrifying grandeur, remind us that the universe doesn't need aliens or asteroids to pose existential threats. Sometimes the most compelling villains are the ones already written into the fabric of reality, waiting unseen in the dark between stars. Some gamma-ray bursts play a cosmic game of hide and seek, flashing into existence with staggering energy, then vanishing without the usual afterglow. These elusive events, dubbed dark bursts, have puzzled astronomers for decades. You'd expect the aftermath of such violent explosions to light up the cosmos for weeks across X-ray, optical, and radio wavelengths. But roughly 30% of detected GRBs leave no visible trace, as if space itself swallowed the evidence whole. The leading suspect, cosmic dust, thick clouds of carbon and silicate particles that act like interstellar smoke screens. When a GRB erupts in a dusty galaxy, these microscopic grains absorb visible light while allowing higher energy X-rays and gamma rays to pass through. The result is an explosion visible only at the extremes of the spectrum, its optical fingerprint smothered before it can reach our telescopes. Imagine witnessing a forest fire through dense fog. You might feel the heat and see flickers through the haze, but the flames themselves remain hidden. That's when NASA's James Webb Space Telescope enters the scene as the universe's ultimate dust-piercing detective. Unlike optical telescopes blinded by these veils, JWST infrared eyes cut through the obscuration like night vision goggles. Infrared light, with wavelengths longer than visible light, slips between dust particles rather than bouncing off them. When JWST turned its gaze to dark burst GRB 220922 last year, it uncovered what Hubble had missed, a faint but unmistakable infrared afterglow, revealing the burst's home in a galaxy choked with stellar debris. The data told a story of a massive star's death in a stellar nursery so dusty, even its final explosion couldn't fully clear the fog. But dust isn't the only culprit. Some dark bursts might originate in the universe's primordial eras, so distant their visible light has stretched into infrared through cosmic expansion, a phenomenon called redshift. Others could involve jets angled just slightly away from Earth, offering a grazed view with weaker afterglows. JWST's ability to peer both through dust and back in time makes it the perfect tool to crack these cases. Already, it's spotted dark bursts linked to some of the earliest galaxies ever observed. Their afterglows redshifted into near invisibility for conventional scopes. The implications ripple beyond astronomy textbooks. Every solved dark burst rewrites our understanding of stellar deaths in extreme environments, from dust-choked galaxies to the universe's first star-forming regions. These stealthy explosions might even outnumber their brighter cousins, suggesting we've been missing a significant chunk of cosmic violence. With JWST on patrol, the era of GRBs hiding in plain sight is finally ending, one infrared revelation at a time. The jets powering gamma-ray bursts don't just unleash raw energy. They're nature's most brutal particle accelerators, flinging matter to velocities so extreme they defy earthly physics. Picture the Large Hadron Collider, humanity's mightiest machine, smashing protons at 99.9999% light speed. Now imagine an accelerator a trillion times more powerful, forged in the wreckage of a collapsing star where magnetic fields twist spacetime itself into a cosmic slingshot. That's the scale of a GRB jet, a chaotic, hyper-relativistic storm where electrons, protons, and even atomic nuclei get whipped to energies that make CERN achievements look like a schoolyard catapult. How does this cosmic demolition derby work? It starts with the black hole's birth. As the star's core collapses, it doesn't just vanish quietly, it spins, dragging spacetime around it like a whirlpool. This rotation, combined with magnetic fields strong enough to shred atoms, transforms the jet into a particle boosting machine. Charged particles spiral along these magnetic field lines, gaining energy with each loop, like a pinball ricocheting through an electrified maze. But here's the twist: the jet's walls aren't smooth. Turbulence and shockwaves ripple through it, acting like speed bumps that violently jolt particles to even higher energies. By the time these particles escape the jet's grip, they're moving so fast their kinetic energy could power a city for centuries. We've actually detected the fallout from these accelerators. Some of the most energetic cosmic rays, subatomic bullets pelting Earth from deep space, carry signatures matching GRB jet physics. These aren't just random particles, they're fugitives from stellar cataclysms, hurled across galaxies by forces we're only beginning to understand. At the Pierre Auger Observatory in Argentina, scientists have traced ultra-high energy cosmic rays back to regions of space where gamma-ray bursts recently flared. It's like finding spent shell casings at a crime scene, the smoking gun linking these rare particles to the universe's most violent explosions. What fascinates physicists is how GRB jets mirror and surpass human-made accelerators. At CERN, we painstakingly guide particles using superconducting magnets in a vacuum. In a gamma-ray burst, nature achieves similar results through sheer cosmic brutality. Gravitational energy becomes magnetic energy, which becomes particle energy, all in a chaotic plasma soup hotter than a trillion suns. Yet both processes, despite their differences, rely on the same basic principle: particles gain energy when pushed by electromagnetic fields, the key distinction. GRB jets operate without walls, without circuits, and with energies that would instantly vaporize any man-made structure. This marriage of astrophysics and particle research is revealing deeper truths. By studying GRB jets, scientists are testing theories about how all high-energy particle accelerators work, from black holes to supernova remnants. Some even suspect these jets might be the source of mysterious ultra-high-energy neutrinos detected by observatories like IceCube in Antarctica. If confirmed, it would prove gamma-ray bursts are multitaskers, cosmic ray factories, neutrino foundries, and light beacons all rolled into one. So the next time you hear about a gamma-ray burst, remember, it's not just a flash in the dark. It's a runaway particle accelerator, a natural laboratory where the universe bends its own rules, and a reminder that even our most advanced technology is just catching up to nature's raw, unbridled power. Among the universe's strangest and most violent objects, magnetars stand out: neutron stars with magnetic fields so intense they could erase a credit card from halfway to the moon. These cosmic powerhouses occasionally unleash starquakes, cracking their ultra-dense crusts and triggering eruptions called magnetar flares. But here's where things get even more extreme. Some of these flares pack enough punch to mimic short gamma-ray bursts, blurring the line between stellar tantrums and full-blown cosmic cataclysms. Take the event from December 2022, when a magnetar designated SGR 1935+2154 erupted in our galactic backyard 30,000 light-years away. For a tenth of a second, it emitted more X-rays and gamma rays than our Sun does in a decade, flashing brighter than the entire Milky Way. At first glance, it looked like a classic short GRB, the kind usually linked to neutron star collisions. But this burst didn't come from a merger. It came from a single, unstable magnetar convulsing under the strain of its own magnetic field, which is a quadrillion times stronger than Earth. The physics behind these eruptions reads like a sci-fi novel. A magnetar's crust, under unimaginable pressure, occasionally fractures. Think of an earthquake, but one where the ground is a crystalline lattice of neutron-rich material harder than diamond. When these starquakes occur, they snap the star's magnetic field lines like overstretched rubber bands, releasing pent-up energy in a blast of radiation. In extreme cases, the flare can accelerate particles to near light speed, creating a gamma-ray spike indistinguishable from the opening act of a neutron star merger. What's fascinating is how rare and revealing these events are. Out of the thousands of short GRBs detected, only a handful have been traced back to magnetars. The most famous, GRB 050925, initially baffled scientists. Its afterglow pointed to an isolated neutron star, not a collision remnant. Later analysis revealed it as a magnetar flare so powerful it briefly impersonated a merger-driven burst. This discovery forced astronomers to expand their GRB playbook. Sometimes, nature fools us with a stellar impersonator. But why does this distinction matter? Because magnetar flares offer a front-row seat to physics at the edge of possibility. Their magnetic fields are so strong they distort the quantum vacuum, creating conditions where light itself behaves oddly. Photons can split and merge in ways impossible under normal circumstances, and the magnetic pressure can literally squeeze atoms into pencil-thin shapes. Studying these flares isn't just about GRBs, it's about probing the limits of how matter and magnetism interact under extremes unreachable in any lab. Yet the biggest question remains unanswered. Could a magnetar flare ever rival a true short GRB in raw destructive power? Theoretically, yes, if the star's magnetic field twisted itself into a knot and then suddenly unraveled, the energy release could approach merger-like levels. Fortunately, such hyperflares seem to be once-in-a-galaxy lifetime events, but in a universe where magnetars exist, it's a reminder that sometimes the most terrifying explosions don't require two stars colliding, just one having a very, very bad day. Scientists are recreating the universe's most violent explosions right here on Earth, not with stars or black holes, but with some of the most powerful lasers ever built. At facilities like the National Ignition Facility in California and the Omega Laser in New York, researchers are firing beams of concentrated light so intense they can, for a fraction of a second, mimic the extreme conditions inside a gamma-ray burst relativistic jets. These aren't just tabletop experiments, they're cosmic crime scene reconstructions, peeling back the physics behind nature's brightest flashes. Take the NIF's record-breaking shot in 2021, where 2 million joules of laser energy equivalent to 500 trillion watts were focused onto a peppercorn-sized target. For a few nanoseconds, that spot became the hottest place in the solar system, hitting temperatures over 100 million degrees. That's hotter than the sun's core, hot enough to strip electrons from atoms and create a plasma state identical to the superheated material screaming through a GRB jet. By studying how these plasmas evolve under such extremes, physicists can test theories about shockwave formation, magnetic field amplification, and particle acceleration processes that are otherwise impossible to observe directly in distant space. The real breakthrough came when researchers noticed their lab-made plasmas were behaving eerily like scaled-down versions of GRB jets. Under the laser's fury, electrons in the plasma started surfing shockwaves at nearly light speed, just as they do in astrophysical jets. Magnetic fields, twisted into knots by the plasma's turbulence, acted like natural particle accelerators, exactly what astronomers suspect powers gamma-ray bursts high-energy emissions. Even the telltale flickering seen in real GRBs, once thought to come from internal collisions within the jet, has been replicated in these experiments through plasma instabilities. What makes these simulations so valuable isn't just their precision, but their control. In space, we see GRBs only after the fact, like detectives arriving at an explosion's smoldering ruins. But in the lab, scientists can tweak variables, laser energy, target composition, magnetic field strength, and watch how the jet responds in real time. One experiment at the University of Oxford even recreated the unique spiral structure seen in some GRB jets by shaping the laser pulse into a corkscrew pattern. The results matched computer models of rotating hypernova, suggesting that even a dying star's spin leaves fingerprints in its gamma-ray scream. Of course, there are limits. No terrestrial laser can truly match the energy of a cosmic GRB. A real burst outshines these experiments by a factor of a quadrillion. But by scaling down the physics while preserving the key conditions, researchers have uncovered surprises. For instance, plasma instabilities once assumed to dampen jet energy might actually turbocharge it, explaining how GRB beams stay coherent across billions of light years. Other experiments suggest that self-generated magnetic fields could be the secret behind the jet's narrow focus, acting like cosmic nozzles to prevent energy from dissipating sideways. The ultimate goal: to bridge the gap between celestial cataclysms and quantum physics. Some teams are now using these plasmas to test ideas about quantum electrodynamics in extreme magnetic fields, conditions where particles start behaving like waves and empty space itself becomes polarized. It's a reminder that gamma-ray bursts aren't just astronomical spectacles. They're natural laboratories where the universe tests the laws of physics at their breaking points. And with every laser shot that echoes their fury, we get closer to decoding the universe's most violent language, 1 nanosecond at a time. The idea that gamma-ray bursts could be artificial deliberate signals from advanced civilizations sounds like pure science fiction. But when you consider the Fermi paradox, the unsettling question of why we haven't found evidence of extraterrestrial intelligence despite the universe's vastness, even wild theories deserve a second look. After all, if an alien civilization wanted to announce its presence across the cosmos, few signals would cut through the interstellar noise better than a gamma-ray burst. A single GRB could outshine every star in its host galaxy combined, making it visible for billions of light years. Imagine a flare gun fired into the cosmic darkness, impossible to ignore. But could nature's most violent explosions really be engineered? The challenges are staggering. For starters, the energy requirements are ludicrous. Generating a burst as powerful as GRB 221009 would demand harnessing the total output of a star like our Sun for trillions of years, something no known technology, no matter how advanced, could feasibly achieve. Then there's the precision problem. GRB jets are incredibly narrow, meaning any civilization trying to use them as beacons would need to aim them deliberately, like threading a needle across intergalactic distances. And if the goal is communication, there's a glaring flaw. GRBs carry no discernible pattern or information. They're cosmic static, not Morse code, yet some theorists refuse to dismiss the idea entirely. One fringe hypothesis suggests advanced civilizations might trigger artificial GRBs by colliding neutron stars, essentially using nature's own blueprint to create detectable fireworks. Another posits that certain repeaters, rare bursts with unusual periodicity, could be signatures of deliberate engineering. Most scientists remain skeptical, pointing out that natural explanations cover nearly all observed GRB behavior. But the debate taps into a deeper truth. When we search for aliens, we often look for signs that mirror our own technology: radio signals, laser pulses, Dyson spheres. Maybe we're missing something far grander. The irony is that gamma-ray bursts, whether natural or artificial, already solve one piece of the Fermi paradox. Their existence suggests that the universe is brimming with catastrophic events capable of sterilizing entire galaxies. If GRBs or similar phenomena are common, they might act as a great filter, wiping out civilizations before they can spread beyond their home systems. This grim possibility turns the beacon idea on its head. What if the reason we don't see alien signals isn't because they're hiding, but because the cosmos itself is a minefield of extinction-level events? Ultimately, the GRB as beacon theory remains firmly in the realm of speculation, but it serves as a reminder that the universe is stranger than we imagine, and that sometimes the most compelling mysteries lie at the intersection of astrophysics and imagination. Whether natural or not, gamma-ray bursts force us to confront fundamental questions about our place in the cosmos. Are we alone? And if not, how would we even know? For now, the bursts keep their secrets, flashing across the dark like unanswered signals in the night. At the heart of every long gamma-ray burst lies a cosmic monster in the making, a newborn black hole. This isn't just any stellar collapse, it's a violent genesis where gravity wins its ultimate victory, compressing a dying star's core into a singularity so dense it bends spacetime into a prison from which not even light can escape. But here's what most people miss: the black hole doesn't just form and sit quietly. It throws one of the universe's most spectacular tantrums, and that tantrum is what we see as a gamma-ray burst. Picture the moment of creation. As the star's core implodes, it doesn't vanish smoothly into the black hole's maw. Instead, the infalling matter swirls into a superheated vortex called an accretion disk, a cosmic whirlpool spinning at nearly light speed. Temperatures here soar to billions of degrees, turning atoms into a soup of plasma so energetic it glows with X-rays. Magnetic fields, twisted into helical coils by the disk's insane rotation, act like particle accelerators, channeling some of this chaos into twin jets erupting from the black hole's poles. These jets, narrower than a laser beam yet stretching light years into space, are the particle cannons behind the gamma-ray burst's lethal brilliance. Simulations reveal just how delicate and brutal this dance really is. Supercomputers modeling these events show the black hole's spin acting like a flywheel, dragging spacetime around it in a phenomenon called frame dragging. This rotation whips the magnetic fields into a frenzy, launching the jets with pinpoint precision. Too little spin, and the jets sputter out. Too much, and they become unstable, kinking like a garden hose turned to full blast. The sweet spot: a black hole spinning at 80 to 90% of its maximum possible rate, fast enough to power the jets but stable enough to keep them collimated across interstellar distances. But the real magic happens in the accretion disk's inner sanctum. Here, turbulence and magnetic reconnection, think of it as cosmic short-circuiting, create pockets of energy that detonate like underwater mines. These explosions within explosions pump extra energy into the jets, explaining why some gamma-ray bursts flicker unpredictably. It's a feeding frenzy where the black hole gorges on stellar debris while simultaneously belching out focused destruction. What's astonishing is how efficient this engine is. Up to 40% of the infalling matter's mass gets converted directly into energy via Einstein's E equals mc squared, far more efficient than nuclear fusion, which powers stars at a measly 0.7% efficiency. That's why a single gamma-ray burst can outshine galaxies. Its central engine is essentially nature's ultimate power plant, running on the purest form of mass-to-energy conversion the universe allows. Yet the black hole's role doesn't end when the burst fades. Long after the gamma rays vanish, the accretion disk continues to glow in X-rays for days or weeks, its fading light a telltale sign of the black hole's lingering appetite. Some bursts even show evidence of late-time energy injections, likely the black hole snacking on last chunks of debris, reigniting the afterglow like a dying campfire fed with fresh kindling. These leftovers are more than just cosmic scraps. They're forensic evidence helping astronomers weigh the black hole, measure its spin, and even estimate how much stellar flesh it devoured during the cataclysm. So the next time you hear about a gamma-ray burst, remember, you're not just witnessing an explosion. You're seeing the birth cry of a black hole, a fleeting moment where destruction and creation collide on scales that dwarf human imagination. And in that collision, the universe reveals its most extreme physics written in gamma rays, sculpted by gravity, and powered by the darkest objects in existence. What if we could get a heads up before a gamma-ray burst detonates its fury across the cosmos? Scientists are working on an early warning system, not using light but ghostly particles called neutrinos that escape the star's collapsing core moments before the gamma-ray fireworks begin. Here's how it works. When a massive star is on the verge of collapsing into a black hole, the insane pressures in its core generate a neutrino flood, trillions of these nearly massless particles streaming outward at light speed. Crucially, these neutrinos punch through the star's outer layers hours before the explosion reaches the surface. That means detectors on Earth could pick up this particle pulse while the doomed star still appears perfectly normal in telescopes. Current neutrino observatories like IceCube in Antarctica already catch high-energy neutrinos from cosmic events, but they're not yet optimized for burst warnings. New proposals aim to change that. The next-generation IceCube Gen 2, slated for construction this decade, would deploy over 10,000 optical sensors across a cubic kilometer of Antarctic ice. When a neutrino interacts with the ice, it creates a flash of blue light called Cherenkov radiation, allowing scientists to trace the particle's origin. The goal: to identify neutrino bursts matching the signature of a collapsing stellar core, then automatically alert telescopes worldwide within seconds. Here's the brilliant part: those precious seconds could revolutionize how we study GRBs. Normally, telescopes only swing into action after the gamma rays arrive, missing the explosion's earliest moments. But with a neutrino heads-up, instruments could already be trained on the target when the first photons erupt. Imagine capturing the exact instant a star's surface ripples from the shockwave, or watching a black hole's birth cry in real time. Some systems, like the Swift satellite, could even repoint mid-burst if given early enough notice. The challenges are formidable, though. Neutrinos rarely interact with matter. Trillions pass through your body every second without a trace, so detectors must be enormous to catch enough signals. False alarms are another hurdle. Distinguishing stellar collapse neutrinos from background noise requires ultra-precise energy and direction measurements. That's why projects like the Pacific Ocean Neutrino Experiment (P1) are exploring complementary approaches using underwater sensor arrays to cross-verify detections. If successful, this early warning network wouldn't just benefit astronomy. Neutrinos from GRBs could help solve lingering mysteries about these particles themselves, like whether they have even a tiny mass or if they oscillate differently under extreme gravity. Every second of advance notice isn't just about beating the gamma-ray clock. It's a chance to peer deeper into the physics governing the universe's most violent births. And in a cosmos where light speed delays mean we're always seeing the past, that split-second warning might be the closest we ever get to witnessing cosmic destruction in real time. Gamma-ray bursts might do more than just illuminate our universe. They could be windows into others. Some theoretical physicists speculate that these cosmic explosions could offer clues about the multiverse, a wild idea suggesting our universe is just one bubble among countless others in an infinite cosmic foam. The connection sounds like science fiction, but when you push the limits of known physics, reality often outpaces imagination. Take the concept of quantum foam, the turbulent froth of spacetime at scales 1 billion times smaller than an atom. Here, according to some theories, tiny bubbles of universes might constantly blink in and out of existence. Most vanish instantly, but under extreme conditions like those in a gamma-ray burst's relativistic jets, these bubbles could theoretically stabilize, creating fleeting portals to alternate realities. It's a long shot, but GRBs unleash energies so concentrated that they momentarily distort the fabric of spacetime itself, warping the quantum vacuum in ways we barely understand. Even more speculative is the idea that certain ultra-high-energy photons detected from GRBs might carry fingerprints of collisions between our universe and others. Some models suggest that if a bubble universe brushed against ours, the energy release could mimic the signature of a short gamma-ray burst, an explosion with no apparent source in our cosmic neighborhood. A handful of anomalous GRBs, like the mysterious GRB 170817A, have defied explanation because they lack host galaxies or afterglows, leaving scientists to wonder if they're glimpses of something beyond our cosmic horizon. Of course, these ideas live on the fringes of physics, where hard data is scarce and imagination runs wild. But that's precisely why GRBs matter. They force us to confront questions at the very edge of comprehension. Whether they're cosmic flukes or multiversal messengers, these bursts remind us that the universe still holds mysteries we're only beginning to articulate. And in those milliseconds of gamma-ray brilliance, we might be catching echoes of realities far stranger than we've dared to dream. Gamma-ray bursts are cosmic fireworks so extreme, they've spawned their fair share of myths, like the idea that these explosions cause supernova. Let's set the record straight. GRBs aren't the instigators of stellar destruction. They're the screams of stars already in their death throes. Think of it like a car crash. The sound of screeching metal doesn't cause the collision, it's the aftermath. Similarly, a gamma-ray burst is the universe's way of broadcasting the moment a massive star's core collapses into a black hole or neutron stars collide. The supernova or hypernova in the case of the most energetic events is the main event. The GRB, just the shockwave's brightest echo. Another common mix-up is the fear that every gamma-ray burst poses an existential threat to Earth. While it's true a nearby burst could strip our ozone layer, the odds are laughably slim. For one, GRB jets are incredibly narrow. Even if a hypernova detonated in our galactic neighborhood, the jet would need to be precision aimed at us like a cosmic sniper rifle. And here's the kicker: the types of stars that produce long GRBs, metal-poor, fast-spinning behemoths, are vanishingly rare in our corner of the Milky Way. Statistically, we're more likely to win the lottery every day for a year than to be hit by a lethal burst. Then there's the sci-fi favorite, the notion that GRBs could be artificial, some alien superweapon. The physics here is brutally clear. Generating even a fraction of a GRB's energy would require harnessing the total output of a star for millennia. And why would an advanced civilization waste such incomprehensible resources on a signal that, by cosmic standards, is as subtle as a flashbang in a library? Natural GRBs already flood the universe with enough gamma rays to drown out any hypothetical alien transmission. Perhaps the most persistent myth is that gamma-ray bursts are unpredictable, random flashes. In reality, they follow strict physical blueprints. Short bursts almost always trace back to neutron star mergers, while long bursts reliably tag the deaths of Wolf-Rayet stars, massive, short-lived giants that shed their outer layers long before collapse. Even their afterglows obey precise patterns, fading in predictable wavelengths over days or weeks. Far from being chaotic, GRBs are cosmic clockwork, their violence governed by equations we're steadily deciphering. The bottom line: gamma-ray bursts aren't cosmic boogeymen or interstellar Morse code. They're nature's way of marking the universe's most violent turning points, a reminder that even in destruction, there's order, beauty, and a story waiting to be told. And as we separate fact from fiction, we uncover something even more thrilling. The real science behind these explosions is stranger and more spectacular than any myth could ever be. The hunt for gamma-ray bursts is about to enter a thrilling new era, thanks to missions like the European Space Agency's Theseus, a cosmic time machine designed to catch the universe's earliest explosions in the act. Slated for launch in the mid-2030s, this satellite isn't just an upgrade, it's a revolution. Imagine having a telescope so sensitive it could spot a birthday candle on the moon, then multiply that by 1 billion. Theseus will peer back to the cosmic dawn, capturing GRBs from the first billion years after the Big Bang, bursts so ancient their light has been stretched into the infrared by the universe's expansion. These aren't just distant flashes, they're fossilized light from an era when the first stars were igniting, and galaxies were little more than twinkles in the void. What sets Theseus apart is its triple-threat instrument suite. Its soft X-ray imager will scan huge swaths of the sky for the telltale X-ray glow of newborn bursts, while the infrared telescope tracks their fading afterglows. even through the thick dust that shrouds the universe's earliest galaxies. But the real game changer is the gamma-ray burst monitor, capable of detecting bursts 10 times fainter than current tools. That sensitivity is key because the most distant GRBs don't just fade. Their light gets redshifted into near invisibility, like a firefly viewed through foggy glass. Theseus cuts through that haze, revealing bursts that would have been missed by Swift or Fermi. The payoff, a clearer picture of how the first stars lived and died. Theorists predict these pioneers were monsters hundreds of times more massive than the Sun, burning pure hydrogen and helium in violent, short lives. When they collapsed, their gamma-ray bursts would have been unlike anything we see today, brighter, longer, and possibly even triggering the ionization of the universe's primordial hydrogen fog. Theseus could catch these mythical explosions in the act, confirming whether they really were the cosmic matchsticks that lit the Dark Ages. But the mission's ambitions stretch beyond GRBs. By mapping the locations of ancient bursts, Theseus will effectively chart the universe's teenage years, a time when galaxies were assembling and the first supermassive black holes were taking shape. Some models suggest early GRBs might have been engines of galactic evolution, their jets heating surrounding gas and either quenching or spurring star formation. It's like discovering that wildfires, long seen as purely destructive, also fertilize forests for new growth. Meanwhile, NASA planned starburst mission aims to complement Theseus by focusing on neutron star mergers. Equipped with gamma-ray spectrometers, Starburst will hunt for the unique signatures of heavy elements like gold and platinum forged in these collisions, a cosmic alchemy we've only glimpsed once before in 2017. Together, these missions could solve a lingering puzzle. How much of the universe's gold comes from GRBs versus mergers? The answer might rewrite our understanding of where Earth's precious metals really originated. And let's not forget the ground-based reinforcements. The upcoming extremely large telescope with its 39-meter mirror will dissect Theseus-discovered afterglows with unprecedented precision, measuring their chemical fingerprints down to parts per billion. It's the difference between identifying a wine by its bottle and analyzing each molecule in the vintage. What makes this new wave of missions so exciting isn't just their technology. It's their potential to turn GRBs from cosmic oddities into essential tools. Like radiocarbon dating for the universe, these bursts could become standard markers for measuring cosmic expansion, testing gravity's laws across billions of light years, and even probing the nature of dark energy. The universe's brightest explosions, it seems, have the darkest secrets left to reveal, and we're finally building the keys to unlock them. You don't need a PhD to contribute to gamma-ray burst research. Some of the most exciting discoveries in astrophysics are happening thanks to everyday people staring at their laptops in pajamas. Platforms like Zooniverse have turned the hunt for cosmic explosions into a global team sport, where anyone with an internet connection can help astronomers sift through mountains of data. It's a modern-day gold rush, except instead of pickaxes, volunteers are armed with curiosity and a mouse click, uncovering hidden gems in the noise of space. Take the story of teacher Hanny van Arkel, who in 2007 spotted a strange green smudge in a galaxy image while classifying data for Galaxy Zoo. That smudge, later named Hanny's Voorwerp, turned out to be a never-before-seen cosmic phenomenon, a ghostly cloud illuminated by the echo of a quasar. Moments like these prove that breakthroughs aren't just for professionals. Right now, projects like Gamma-Ray Burst SkyMap let volunteers scan data from NASA's Fermi satellite, tagging unusual bursts or patterns that might have slipped past automated algorithms. These human eyes catch what machines miss: subtle quirks in light curves or oddball afterglows that could hint at new physics. What makes this crowdsourcing revolution so powerful is scale. A single gamma-ray burst can generate terabytes of data across multiple wavelengths. Telescopes like Swift detect hundreds of bursts yearly, leaving researchers drowning in information. But with thousands of volunteers worldwide, retirees in Tokyo, students in Nairobi, night shift workers in Berlin, the workload fractures into manageable pieces. It's like having a global search party scanning every inch of the cosmic forest for flashes of light. The tools are surprisingly intuitive. On Zooniverse's Burst Chaser project, users classify GRB light curves by shape, spiky, smooth, or erratic, helping scientists correlate patterns with explosion mechanisms. Other platforms train volunteers to spot kilonova candidates in telescope images, potential evidence of neutron star mergers. There's even a citizen science app that lets your phone analyze Fermi data in the background while you scroll through social media. Every click adds to a crowdsourced map of the universe's most violent events. But this isn't just busy work. In 2021, amateur classifiers helped identify a rare, ultra-long GRB that lasted nearly 10,000 seconds, a clue that some bursts might come from entirely new stellar death scenarios. Another team of volunteers discovered a peculiar burst with rhythmic flickering, suggesting a black hole's accretion disk might have wobbled like a spinning top before going silent. These finds aren't just footnotes, they're rewriting textbooks. The beauty of citizen science is how it demystifies research. Participants aren't just clicking buttons, they're joining live discussions with astronomers, attending virtual conferences, and even co-authoring papers. When the James Webb Space Telescope spots a GRB afterglow, it's often citizen scientists who first flag unusual spectral lines or chemical signatures. They're not just helping science, they're living it, turning coffee breaks into cosmic explorations. So if you've ever dreamed of uncovering a cosmic secret, now's your chance. The next gamma-ray burst mystery might not be solved by a telescope or a supercomputer, but by someone like you staring at a screen, making the connection that changes everything. After all, the universe doesn't care who cracks its code, only that someone's paying attention. Gamma-ray bursts might do more than reveal the lives of stars. They could crack open one of physics' greatest mysteries, the nature of quantum gravity. At their heart, these cosmic explosions are natural laboratories where energies reach levels so extreme that space and time themselves might behave differently. According to Einstein, all light travels at the same unchanging speed, the famous c in E equals mc squared. But some theories suggest that at the tiniest scales, where gravity and quantum mechanics collide, photons of different energies might actually move at slightly different speeds through the fabric of spacetime. Detecting this effect would revolutionize our understanding of reality, and gamma-ray bursts are the universe's perfect stopwatch for the test. Here's why GRBs are ideal for this search. When a burst erupts, it floods space with photons across an enormous energy range, from low-energy radio waves to gamma rays with 1 trillion times more punch. According to conventional physics, all these photons should arrive at Earth simultaneously after their multi-billion-year journey. But if quantum gravity theories are correct, the highest energy gamma rays might lag behind their lower energy counterparts by mere milliseconds. That delay would be the smoking gun, evidence that spacetime isn't smooth at quantum scales, but grainy, like a cosmic pixelation only visible to particles moving at near light speeds. The challenge is catching these subtle time differences. GRB photons must traverse half the universe to accumulate a measurable delay, and even then, the effect would be vanishingly small. Think a few thousandths of a second over billions of light years. That's where missions like the Fermi Gamma Ray Space Telescope become crucial. Fermi's ultra-precise detectors can timestamp photon arrivals down to microseconds, allowing scientists to compare high and low-energy light curves with unprecedented accuracy. When Fermi observed GRB 090510 in 2009, researchers scrutinized its photons for any sign of energy-dependent delays. The result: no detectable difference, but that non-detection was itself valuable, ruling out entire classes of quantum gravity models. The implications of a positive detection would be staggering. If gamma rays consistently arrived later than expected, it would suggest spacetime has a fundamental foaminess at scales a billion trillion times smaller than an atom, a realm where black holes might flicker in and out of existence and gravity merges with quantum weirdness. Some theories even predict that the delay should increase with the photon's energy, offering a way to test competing quantum gravity frameworks. Imagine being able to weigh in on the debate between string theory and loop quantum gravity just by studying the afterglow of a cosmic explosion. Yet the hunt isn't without complications. Interstellar and intergalactic space isn't empty, it's filled with charged particles and magnetic fields that can also slow down light, mimicking quantum gravity effects. Disentangling these contaminants requires analyzing bursts at different distances and through varying cosmic environments, like comparing stopwatch readings across multiple racetracks. That's why recent studies focus on short GRBs from neutron star mergers, whose cleaner electromagnetic profiles make them better probes than their longer, messier cousins. What makes this search so thrilling is its audacity. Gamma-ray bursts born from stellar catastrophes might illuminate physics far beyond stars, tapping into the universe's most fundamental layer. Every new burst Fermi catches adds another data point, another chance to spot the subtle fingerprints of quantum gravity, and if that signal ever appears, it would mean these cosmic explosions aren't just the universe's brightest flashes, they're its most precise rulers, measuring the texture of reality itself. Gamma-ray bursts don't just light up the cosmos, they also sing. Scientists have found a way to listen to these cataclysmic explosions by converting their gamma-ray data into sound, revealing rhythms and patterns invisible to the eye. This process, called sonification, transforms raw numbers into an auditory experience, letting us hear the universe's most violent events in a startlingly intimate way. Picture this: the jagged spikes of a gamma-ray burst's light curve, usually seen as a graph on a screen, become a cascade of sharp, percussive notes, each pulse a stellar heartbeat, each flare a scream of energy. The result isn't just artistic, it's a powerful tool for discovery, uncovering hidden structures in the chaos. NASA Chandra X-ray Center pioneered this approach, sonifying data from telescopes like Fermi and Swift. One project took GRB 130427A, a burst lasting over 20 hours, and stretched its X-ray emissions across a musical scale. The high-energy peaks became piano keys, while the lingering afterglow faded into a deep, resonant hum. What emerged wasn't random noise, it was a cosmic symphony with repeating motifs, hinting at oscillations in the black hole's accretion disk that would have gone unnoticed in visual graphs. These auditory clues have led researchers to re-evaluate how energy dissipates in GRB jets, suggesting turbulence plays a bigger role than previously thought. But why does this work? Human ears are surprisingly adept at detecting subtle patterns in sequences. Think of recognizing a familiar voice in a crowded room. By translating gamma-ray fluctuations into sound, astronomers can pick up on rhythmic variations or asymmetries that might slip past the eye. In one case, a sonified short GRB revealed a faint, double-peaked structure in its light curve, evidence of a neutron star merger's shockwaves echoing through interstellar space. Without hearing that split-second echo, scientists might have dismissed it as statistical noise. The creative possibilities are just as thrilling. Composers have collaborated with astrophysicists to turn GRB data into immersive soundscapes. One piece, Collision, uses the timings of photons from GW 170817, the famous neutron star merger, to drive a pulsating electronic score. The gravitational wave signal's rising pitch mirrors the star's death spiral, while the gamma-ray burst's abrupt cutoff becomes a jarring silence. It's science as art, blurring the line between analysis and emotion. For educators, sonification is a game-changer. Students struggling to interpret spectral graphs can hear the difference between a long GRB's sustained roar and a short burst staccato crack. NASA even offers online tools letting anyone convert telescope data into sound, turning cosmic phenomena into a playground for the curious. Imagine a classroom where kids manipulate sliders to remix a gamma-ray burst, discovering how changing energy levels alters its musical signature. Yet the most profound impact might be accessibility. Sonification opens the cosmos to blind and low-vision researchers, offering a tactile way to engage with data. Projects like the Astrosonification Initiative are refining these techniques, mapping brightness to volume, frequency to energy, creating a universal language for the universe's extremes. So the next time you see a gamma-ray burst's jagged graph, remember, there's music hidden in those spikes. In the hands of scientists and artists alike, these explosions become more than just light. They're echoes of creation itself, waiting to be heard. Imagine watching a gamma-ray burst unfold not from the safety of Earth, but from a spaceship hovering dangerously close to the explosion source. To your horror, the universe around you would begin playing tricks on your perception of time itself. This isn't science fiction, it's one of the most mind-bending consequences of Einstein's theory of relativity, where gravity doesn't just bend space but stretches time like taffy. At the heart of every long gamma-ray burst sits a newborn black hole, an object so dense its gravitational pull warps the very fabric of reality. For an observer brave or foolish enough to orbit near this cosmic maelstrom, time would appear to slow down dramatically compared to someone watching from afar. The mind-blowing part, the entire gamma-ray burst, which we see as lasting minutes from Earth, might unfold over hours or even days from their warped perspective. It's like two people watching the same explosion, one through a normal window and the other through glass that slows down light itself. This phenomenon, called gravitational time dilation, becomes extreme near these stellar catastrophes. The mathematics reveal just how drastic the effect would be. For every second that ticks by near the black hole's event horizon, thousands of seconds could pass on Earth. The jet material screaming outward at 99.9% light speed adds another layer of time distortion due to special relativity, an effect called time dilation from velocity. Put simply, the faster you move through space, the slower you move through time compared to someone at rest. Here's where it gets truly bizarre. An astronaut in this nightmare scenario wouldn't perceive their own time slowing down. To them, their watch would tick normally and their thoughts would flow at the same pace. But if they could somehow observe Earth through a telescope, they'd see our planet's history spooling forward like a videotape on fast forward. Meanwhile, observers on Earth would see the astronaut moving in agonizing slow motion, their signals arriving at increasingly stretched intervals. This two-way time warp was famously illustrated in Christopher Nolan's Interstellar, where hours near a black hole equaled years elsewhere, but gamma-ray bursts take this to even more extreme levels. The practical implications of this time stretching are profound for how we study these explosions. When we detect a gamma-ray burst's afterglow lasting weeks, we're seeing the event through our Earth-based time frame. But near the source, the actual processes powering that afterglow might be unfolding over vastly different timescales. This explains why some bursts appear to stall in their light curves. What we interpret as a sudden energy injection could actually be a relativistic effect, with material from deeper in the gravity well finally reaching our viewpoint after what was, for it, a much longer journey. Perhaps most astonishing is how this time warping affects the burst's very emission. The highest energy gamma rays produced in the deepest gravitational wells near the black hole experience more time dilation than lower energy photons created further out. This creates an energy-dependent echo effect in the light curve, a subtle signature that sophisticated telescopes like Fermi use to map the explosion's structure. In essence, we're not just seeing a blast of radiation, we're decoding the space-time warpage around a newborn black hole using light itself as our probe. The next time you see an artist's impression of a gamma-ray burst, remember those beautiful jets are more than just streams of particles. They're rivers of time, carrying with them the stretched seconds of a place where gravity rules supreme, and the universe's clock ticks at a pace we can scarcely imagine. Spending billions to study explosions in distant galaxies while wildfires rage and oceans rise might seem like a paradox, but that tension sits at the heart of scientific progress. Gamma-ray burst research exists in a delicate balance between the pursuit of pure knowledge and the pressing demands of terrestrial crises. Consider this: a single GRB observatory mission like SWIFT costs roughly $400 million to build and launch, the same price tag as a high-speed rail project serving 500,000 commuters daily, or a state-of-the-art desalination plant capable of providing clean water for an entire city. The ethical question isn't just about dollars, it's about opportunity costs. What do we sacrifice when we point our resources toward the cosmos instead of our own planet? Yet dismissing fundamental space science as frivolous misses a crucial point. Many of modernity's most transformative technologies trace their origins to curiosity-driven research. The same quantum physics that explains gamma-ray bursts also gave us MRI machines. The precision optics developed to study GRB afterglows now guide laser eye surgery. Even Wi-Fi emerged from radio astronomy techniques honed while studying distant cosmic events. When scientists began tracking gamma-ray bursts in the 1960s, they weren't thinking about medical imaging or global communications networks. They were chasing a mystery. But history shows that deep exploration of the universe's extremes inevitably ripples back to Earth in unexpected ways. The debate sharpens when comparing GRB research to climate science budgets. NASA's entire Astrophysics division receives about $1.5 billion annually, roughly what the U.S. spends on climate monitoring every 3 weeks. Critics argue this imbalance reflects skewed priorities, especially when climate models urgently need refinement, but this framing creates a false dichotomy. The technologies developed for GRB detection, ultra-sensitive satellite sensors, advanced spectroscopy, machine learning algorithms to sift through cosmic noise, are now being adapted to measure atmospheric carbon with unprecedented precision. The same orbiting telescopes that catch gamma rays from colliding neutron stars also monitor deforestation rates and methane leaks. Scientific infrastructure, it turns out, rarely serves just one master. Perhaps the strongest argument for GRB research lies in its power to unite humanity under a shared cosmic perspective. When the James Webb Space Telescope captured light from a 13-billion-year-old burst in 2023, it wasn't just data. It was a visceral reminder that we're part of something vastly grander than political borders or quarterly earnings reports. In an era of fragmented attention and short-term thinking, gamma-ray bursts offer something increasingly rare, or that emotional resonance has tangible value, inspiring new generations of scientists, engineers, and dreamers who will tackle problems we can't yet imagine. But awe alone isn't enough. Accountability matters. The astrophysics community has gotten creative about stretching resources, like repurposing military satellite components for civilian telescopes or sharing observational time across international teams. Crowdsourced data analysis projects now allow amateur scientists to contribute meaningfully from their laptops, democratizing what was once the domain of elite institutions. These innovations suggest a middle path, pursuing cosmic questions while maximizing real-world spillover effects. The ethics of gamma-ray burst research ultimately hinge on a deeper question: what kind of civilization do we want to be? One that only fixes immediate problems, or one that also peers over the horizon? The answers aren't simple, but the conversation itself is vital. After all, the same universe that births these spectacular explosions also gave us the curiosity to understand them, and perhaps that's the most compelling argument of all. For astrophysicist Dr. Neil Gehrels, the discovery of gamma-ray burst 120903 wasn't just another data point, it was a white-knuckle chase against time itself. Working at NASA Goddard Space Flight Center in 2012, his team received an automated alert from the Swift satellite at 3:26 a.m., a long burst flaring up near the constellation Camelopardalis. What happened next was pure adrenaline, sprinting to the lab in pajama pants, coordinating with observatories across 3 continents, and manually overriding telescope schedules to catch the afterglow before it vanished. The payoff, a 30-hour marathon of data collection that revealed this burst, was the most distant ever recorded at the time, a flash from when the universe was barely 800 million years old. That moment, Gehrels later said, was like hearing the cosmos whisper its secrets directly into his headset. Not all eureka moments happen in control rooms. For University of Leicester researcher Dr. Kim Page, her breakthrough came during a mundane grocery run. Her phone buzzed with a Fermi satellite alert for GRB 130331a, a short burst suspected to be from a neutron star merger. With no laptop, she dictated coordinates to her collaborator over a crackling line while standing in the cereal aisle, then raced home to analyze data that ultimately showed the burst's peculiar double-peaked light curve, evidence of shockwaves echoing through the merger's debris field. That split-second decision to prioritize science over breakfast cereal helped confirm key predictions about how these collisions forge heavy elements. The emotional toll of this work surfaces in unexpected ways. Dr. Ido Berger at Harvard recalls the heartbreaking night his team lost GRB 150206 to bad weather. After 12 hours of flawless coordination from Namibia's HESS telescopes to the Very Large Array in New Mexico, a storm rolled over Chile's Gemini Observatory just as the afterglow reached peak brightness. All they could do was watch on live feeds as their hard-won target disappeared behind clouds, knowing the data might never come again. These aren't just professional setbacks, they feel personal. Berger keeps a screenshot of that failed observation on his office wall as a reminder science doesn't always reward effort, but persistence rewrites the odds. Then there are the sleepless triumphs like Dr. Krisa Kuvaliotu's legendary 50-hour shift during the Batsy era in the 1990s, when her team noticed a strange subclass of bursts with softer emissions later dubbed X-ray flashes. She refused to leave the console until she'd manually verified every signal wasn't instrumentation error. Her stubbornness paid off. Those oddballs turned out to be GRBs viewed off-axis, proving the explosions emit different wavelengths depending on observation angle. Colleagues still joke about finding her asleep at the keyboard, hands frozen mid-keystroke, surrounded by empty coffee cups and scrawled equations. What unites these stories isn't just passion, it's the visceral understanding that every burst is a limited time offer from the universe. Dr. Eleonora Troja, who led the follow-up of the historic neutron star merger GW 170817, describes the weeks after that detection as cosmic vertigo. Working on 3 hours of sleep per night, her team raced to capture the Kilonova's fading light across 17 telescopes. One memory sticks with her. At 4 a.m. in Arizona's Kitt Peak Observatory, watching the first spectra reveal telltale strontium absorption lines, proof that neutron star collisions really do forge heavy elements. In that bleary-eyed moment, holding printouts still warm from the plotter, the abstract became tangible. The gold in her wedding ring, the platinum in her watch, might have begun their existence in just such a cataclysm billions of years ago. These aren't distant heroes in lab coats, they're people who have missed birthdays, endured divorce, and occasionally cried over corrupted data files. Dr. Fiona Harrison, principal investigator for NASA's New Star Telescope, once spent 36 straight hours troubleshooting a malfunctioning spectrometer during GRB 121202A's critical early afterglow phase. The fix, a literal kick to the equipment rack, a desperation move that somehow realigned a loose circuit board. the data that followed helped prove some bursts contained previously undetected high-energy components. Harrison's takeaway: sometimes science responds to brute force as much as brilliance. What keeps researchers coming back isn't just the thrill of discovery, it's the camaraderie forged in these pressure cookers. Swedish astronomer Dr. Jesper Solomon still laughs about the time his team accidentally triggered a university's fire alarm at 2 a.m. while celebrating a successful observation. Huddled outside in pajamas with evacuation sirens wailing, they realized their burst of excitement had literally awakened the entire campus. Yet that shared absurdity bonds them tighter than any publication credit. The human side of GRB science reveals an uncomfortable truth. For all our advanced tech, these cosmic explosions still demand old-fashioned grit, late nights. Missed flights, busted equipment. The young graduate student who spent her honeymoon analyzing data because a once-in-a-career burst flared during her Bahamas trip. These aren't just sacrifices, they're choices that redefine what it means to be present in a universe where the most extraordinary moments are fleeting by design. And when the stars align, when the data flows clean and the universe cooperates, the payoff isn't just knowledge. It's the electric certainty that for one brief, shining moment, you held history's newest chapter in your hands. Gamma-ray bursts are far more than just flashes in the cosmic dark. They are the universe's ultimate power players, shaping galaxies, seeding the cosmos with the building blocks of planets and life, and forcing us to rewrite the laws of physics. These explosions don't just destroy, they create. Every burst leaves behind a legacy, scattering heavy elements like gold and platinum across interstellar space, elements that might one day end up in the circuitry of our phones or the rings on our fingers. They're the cosmic furnaces where matter is pushed to its limits, where black holes are born, and where gravity and quantum mechanics collide in ways we're still struggling to understand. But GRBs aren't just about the past, they're keys to the future of astronomy. Each new burst we detect peels back another layer of the universe's mysteries, from the behavior of matter at near light speeds to the structure of spacetime itself. The next big burst could be the one that shatters our current models, revealing secrets about dark energy, the multiverse, or even the true nature of gravity. It might come from the edge of the observable universe, carrying whispers of the first stars, or from our own galactic backyard, reminding us just how dynamic and dangerous the cosmos can be. What makes these explosions so thrilling isn't just their raw power, but their unpredictability. A burst could light up the sky tonight, next week, or a century from now. And when it does, astronomers around the world will drop everything to chase its fading glow, racing against time to decode its message. That's the beauty of gamma-ray bursts, their cosmic wild cards, keeping us perpetually on our toes, forever reminding us that the universe is stranger and more violent than we can imagine. So here's the takeaway: the next time you look up at the night sky, remember that out there, right now, a star could be collapsing, neutron stars could be spiraling toward collision, and a black hole could be forming, ready to unleash a beam of energy so bright it outshines galaxies. The next big burst might be hurtling toward us at this very moment, carrying answers to questions we haven't even thought to ask yet. Stay curious, stay watchful, because the universe isn't done surprising us. Now, over to you. What's your favorite cosmic explosion? A supernova, a kilonova, or maybe something even more extreme? Drop it in the comments, and let's geek out over the universe's most spectacular fireworks together. And who knows, the next time a gamma-ray burst lights up the sky, it might be you spotting it first. Keep looking up.